Alright, so I didn't quite get a chance to talk about one of your questions in your homework in class on Thursday. And I just wanted to kind of talk through the reasoning we use, how you would draw a picture for this. There is a video attached to this, but it's not me talking, so it can be a little bit difficult, and having two videos is always better than one. So let's take a look at this. I believe this is question 3 on homework chunk 1 due on Sunday. And we've got a physical plant at the main campus of a large state university receives daily requests to replace fluorescent light bulbs. The distribution of the number of daily requests is bell-shaped and has a mean of 43. So because this is talking about something being bell-shaped, we could also potentially say that it is normal, especially since it has this statement down here. But that means that the mean, we use that symbol for the mean here, mu. The mean is 43. And the standard deviation is 9. Now we didn't talk about this symbol, sigma. It's like S. But it's kind of like the difference between mu and x bar and S and sigma. So the standard deviation, S, sigma, is 9. Okay? Meaning that on average, those light bulbs, on average, the number of light bulbs distributed differs by about 9. So then it says, using the 68, 95, 99.7 rule, what's the approximate percentage of light bulb replacement requests numbering between 34 and 43? Now yours is going to be different because these numbers do get randomized, but we can still use this question to show you how we would talk about this. So let me draw a normal distribution, which will not be perfect, but it'll be fine. That's good enough. Okay. And then in any normal distribution, any perfectly bell-shaped distribution, the mean is always in the middle, every single time, perfectly in the middle. So this ends up putting 50% on each side. So 50% of the light bulbs are over here, and 50% of the light bulbs are over here. So we'll just put in that 43 light bulbs there. And then the way each standard deviation is laid out in this type of distribution, the first one, if you can see how this is kind of curving down and then it changes to curving up, the first one happens right between those two things. If you've taken some of the math classes on campus where you talk about concavity, it's where concavity changes. You don't need to know that. You just need to put a line in there, and really it doesn't matter where you put it in, to me, so long as you're understanding that it's a standard deviation. So if one standard deviation is 9, and I'm going up 9 from 43, that is 52. And if I go down 9 from 43, that is 34. Okay, and I'm going to go out 3 standard deviations here because that's kind of what we always talk about with a normal distribution. So there's one more, and there's another one. The only reason why I know where to put those lines is because of how far away this is. So these should all be the same distance because I'm going the same amount of space. This would be 61 and 70. Do the same thing over here. Going down, we'd have 25 and 16. Okay, so now each of these are 9 away. These are my standard deviation. This idea that 68%, so the 68, 95, 99.7 rule, it's saying 68% of your light bulbs are in here. Okay, they're within 34 and 52, or 68% of the daily distribution amount is between 34 light bulbs and 52 light bulbs. Between 25 and 61 light bulbs, that'd be 95% of our daily distribution amounts. Total, that includes the 68% in the middle. And then if we go all the way out between 16 light bulbs and 70 light bulb, that accounts for 99.7% of daily distribution amounts. Now, that's useful, but it is a little bit more helpful to understand than how we get different amounts going out. If this is 68% and it's cut in half, this would have to be 34% and 34%. From there going out, taking what's left over of 95% and splitting it up between these two here, I get